Friends, welcome to lecture 23, which is plastic analysis 3, where we will learn few examples to estimate collapse load. We will use both the static theorem and the kinematic theorem to solve the problems. Okay? We will start with simple examples and see how we can understand these theorem applications. Okay? So, example 1. We consider a fixed beam with central concentrated load we call this load as W. Okay. So, let us say I have a beam which is fixed at both the ends with a central concentrated load W. Let me name the points as A, B and the midpoint as C, and we say this span is equal and this is L, E, IA. Okay. So, as per the static theorem, we have first to draw the admissible bending moment diagram. So, how do we do that? For a fixed beam, we know if this is my baseline, so there is a fixed moment which is equal to W L by 8. Okay, negative bending moment. Then there is a positive bending moment which is the midspan, which is equal to WL by 4. Okay. What I do, I superimpose these on the same side. So, I draw the negative bending moment diagram here and the positive bending moment diagram, I just swap it like this. Okay. Okay. So, this is negative and this is positive, again negative. Okay. We already know that this value is WL by 4, right. So, now where are the critical sections here? The critical sections are at 3 different places. Let us mark them. The critical sections can be here, can be here, can be here. Okay. So, what is the static degree of indeterminacy for this problem? Let us ask a question. What will be the static degree of indeterminacy for this problem? The static degree of indeterminacy for this problem is 2 by neglecting axial deformation, that is 4 are the unknowns: moment, reaction, moment, reaction. There are 2 equations of equilibrium, sigma Fy0 and sigma m0. So, the degree of indeterminacy becomes 2 by neglecting axial deformation. Okay. So, I need how many hinges to get a mechanism? I need 3. Let us say these are my 3 places where the hinges can form. So, the governing equation now going to be 2 MP, because this is also MP, This is also MP, hinges is formed here. So, 2 MP should be equal to WL by 4, am I right? Therefore, WC, which I say W, will be 4 into 2 MP by L, which is 8 MP by L. So, that is my collapse load. Okay. Ultimately, we assume that hinges are formed at 3 places. Hinges are formed at A, B and C, making it as a complete mechanism. Is it not? I need 3 hinges. I got 3 hinges. On the other hand, let us try to solve this problem using kinematic theorem. So, I have a fixed beam subjected to central concentrated load W. The locations are A, B and C. Okay. Let me now assume a mechanism, right. So, the assumed mechanism is a beam mechanism. So, I have one rotation here, another rotation here and another rotation here. By symmetry you will see this is 2 theta, is it not? So, I need 3 hinges. Let us assume the hinges here, here and here, which are marked in this figure also. Okay. So, now let us see what is the external virtual work. External virtual work is load into displacement. Let us call this as del. What is the internal virtual work? Internal virtual work will be the work done by the plastic hinges and its rotation, which will be MP into theta, which is at A, plus MP into 2 theta, which is at C, plus MP into theta is at B, which gives me 4 MP theta. So, let us equate external virtual work to internal virtual work. So, there are 2 unknowns here, del and theta, but in the figure they are connected. One can say very well, if the span is L, okay, can say for small rotations, tan theta, which is theta, which is actually del by L by 2, which is 2 del by L. So, substituting back here, W into del will be 4 MP into 2 del by L. So, del goes away, I get W C as 8 MP by L, which is same as this. So, friends, both the theorems will ultimately converge to give you the same answer if the problem is simple. Okay. So, both methods or both procedures give you the same answer, okay, in this example. Now, let us take another problem. Let us say a fixed beam is loaded with uniform distributed load of intensity W per unit length. Okay, obtain the collapse load. So, let us do that. Let us say I have a fixed beam subjected to uniform distributed load over a span of L EI. Let us mark this as A and B. There is a critical section at the center, which will be C, because we all know for a beam under uniform distributed load, the maximum moment can also occur at the midspan of the beam. Okay. So, what we should do in static theorem? We must first draw the static admissible bending moment diagram, the static method, and this is the kinematic method. Okay. Let us draw that. So, I am drawing statically admissible bending moment diagram. So, let me draw the fixed end moment diagram separately. We all know this intensity is WL square by 12, standard first semester engineering mechanics. Then let me superimpose the bending moment diagram of this, which will be equal to WL square by 8, am I right? So, now the net bending moment diagram is what I have here. Right, out of which this is positive, this is negative, this is negative. So, this neutral line has shifted to this line, is it not? Okay. So, now we have drawn a statically admissible bending moment diagram. Okay. Let me then do for the statically admissible bending moment diagram. Let us analyze this. Let us first ask a question, how many NP is required for this beam? It is a fixed beam, it has got static degree of indeterminacy as 2. So, we need 3 hinges to make it as a mechanism. So, let us assume these hinges are at A, B and midspan, which is C. Okay. So, now I have a hinge here, I have a hinge here, I have a hinge here, right. Now, I say there is a hinge here, there is a hinge here also, is it not? So, I should say 2 MP will be now equal to WL square by 8. So, which will give me WC as 16 MP by L square. Okay. Which is my collapse load. Let us try to do this problem using kinematic theorem, a fixed beam under uniform distributed load for a span of L and EI. Okay. Let me try to draw the mechanism. Let us say the hinges are allowed to form at 3 locations, one at the midspan, and therefore, this becomes my assumed mechanism. So, one hinge here, one hinge here and one hinge here. Now, let us talk this deflection as del. Let us say this rotation is theta. Okay. Now, let us see what is the external virtual work. So, the external virtual work is done by the load on this area. So, it is nothing but if it is UDL, it is half into base into height into W, which will be WL del by 2. Internal virtual work will be equal to MP into theta, which will be MP into theta, which will be at A, plus MP into 2 theta, which will be at C, which is the midspan of the member, plus MP into theta at B, which becomes 4 MP theta by L. So, by principle of virtual work, I must equate external to internal virtual work. So, W L del by 2 should be 4 MP theta by L. Okay. So, from the figure we know that tan theta is del by L by 2. So, theta becomes 2 del by L. Let us substitute that. So, W into L del by 2 is 4 MP 2 L, so del goes away. Okay. So, that becomes 16 MP by L square, which is WC, which is same as this. So, I get the same collapse load by both the methods if the problem is simple where I can draw the statically admissible bending moment diagram easily, I can assume a perfect collapse mechanism easily, and I can get the same answer by both the methods. And friends, you will also notice that there was no iteration involved. In one stretch we got the answer. You may be wondering, when will the iteration come? Okay? When you have got more than one collapse load obtained from the analysis, okay, then the iteration will start. Let us do another interesting problem where I have a simply supported beam subjected to eccentric load. So, let us say I have a simply supported beam, one end on hinges, other on roller. I have a load which is eccentric. So, this is A and this distance is B. Of course, the span of the member is L and the member has got EI property. Let me draw the statically admissible bending moment diagram. Let us first ask, what is the degree of indeterminacy for this beam? It is 0, is it not? Nil. So, how many plastic hinges I need? I need only one plastic hinge. Where it can form? It can form, let us say this is my A, this is my B and C. So, it can form only at C. It cannot form at A and B because A and B are already hinged connections. So, let us draw the bending moment diagram. So, the hinge can form only at one point, that is here, and we all know that value will be W A B by L. I think we know how to compute this, is it not? So, this is the point where the hinge is formed. Therefore, I can say MP is W A B by L. Therefore, WC is a collapse load will be MP into L by AB, which will be MP into A plus B by AB. So, that is my collapse load, no iteration, straightforward solution. Let us do this using kinematic theorem. Let us draw the admissible collapse mechanism. Here is going to be a beam mechanism. Let us draw that. So, hinges can form only at one location, that is here. Here there are no hinges, please understand that. Now, you may wonder how I am drawing the hinges. Very interesting, friends. If I draw a circle which is unfilled, okay, this is a structural hinge. If I form a circle with filled, this is called plastic hinge. So, these two are structural hinges where the moment is equal to 0. This is a plastic hinge where the moment is equal to MP. So, now since it is unsymmetric the load, this will be theta 1 and this angle will be theta 2 and this rotation will be theta 1 plus theta 2 by simple geometry. Okay. Now, we also know that theta 1, let us call this value as del. So, del by A. So, that is del equals A theta 1, theta 2 is del by B, which means del is also equal to theta 2 into B. Okay. So, let us say the external virtual work done for this problem is W into del. The internal virtual work for this problem is MP into theta 1 plus theta 2, which will be equal to MP into del by A plus del by B, where we say it is MP del A plus B by AB. Okay. So, we should equate this. W del is MP del A plus B by AB. So, del goes away. So, WC is MP A plus B by AB, which is same as we have here. Okay. So, we are able to estimate quickly the collapse loads using both the theorems without iteration, because in both the assumed mechanism or the bending moment diagram, the critical sections are easily identifiable and we are able to mark the location of plastic hinges conveniently without any ambiguity, right. The confusion will come only when it is either a partial collapse mechanism or an over collapse mechanism. Okay. Let us quickly find out another example where is a simply supported beam with central concentrated load. Okay. Let us do that. So, I have a simply supported beam with a central concentrated load W over a span of L comma EI. So, we know the number of plastic hinges required for this problem is 1, because the degree of indeterminacy is 0, and that will be forming the hinge at this point. Let us draw the statically admissible bending moment diagram, which will be this, and this value is W L by 4. Okay. So, let us quickly find out what will be my MP. MP will be W L by 4, therefore, WC will be 4 MP by L, which is straightforward. Let us do the same problem using kinematic theorem. Let us draw a mechanism. We know that the hinge will form here, and here at these two locations there will be structural hinges. Or let us draw it the other way. Let us draw it the other way. Here there will be structural hinges and here there will be plastic hinge. So, this is theta, this is 2 theta, this is theta. I call this as del and the load is W. Okay. So, the external virtual work will be W into del. The internal virtual work will be MP into 2 theta which is at C. So, this is A, B and C. We also know theta is del by L by 2. So, theta is 2 del by L. So, equating external virtual work to internal virtual work, W into del is MP into 2 theta, which will be MP into 2 del by L. So, del goes away. So, that is 4 MP by L, which is exactly same as this. So, that is WC, is it not? So, these are simple problems where we are able to find out the collapse load straight away without any iterations. Okay? Now, let us quickly compare with this understanding the plastic and elastic analysis. Okay? Let us say what are the advantages and disadvantages of plastic analysis. Let us say the advantages. The plastic analysis enables effective utilization of the entire cross section of the member by completely plasticizing the section. 2. Plastic analysis increases the load capacity of the system. 3. Material strength is well utilized. 4. Factor of safety is enhanced by the shape factor. We already derived these equations, or not? What are the demerits of plastic analysis? The disadvantages could be the member will be subjected to excessive deformation. In fact, it is subjected to plastic deformation. Okay? Since this method demands redistribution of moments between the critical sections, this method is useful only to statically indeterminate structures. Of course, it is applicable to form dominant design structures as well. Okay, the system undergoes excessive deformation. Let us quickly compare the plastic and elastic analysis. Okay. Let us say in elastic analysis, what do we do is, we first satisfy something called equilibrium condition. It states that the structure under any load combination should remain in static equilibrium. Okay. The second is compatibility condition. Which states that deformation of different fibers in a given cross section should be compatible with each other to deform freely. The third condition is called limit stress condition. This condition states that the maximum stress in the extreme fiber should not cross yield stress. Relatively, what are the equivalent conditions in plastic analysis? The first condition equivalent to this is mechanism condition. According to this condition, ultimate load or collapse load is reached when mechanism is formed. Two, equilibrium condition. This states that the structure should remain in equilibrium with the applied loads even after the formation of mechanism. Third condition is the plastic moment condition. According to this condition, in any fiber at any cross section, the developed stress should not exceed sigma y and the moment cannot exceed mp. Okay. So, quick comparison between these two method of analysis. Having said this, let us now look at examples where some tricky iteration is also involved. Let us do special examples where obtaining the collapse load is not that easy, okay, slightly tricky. We will take an example 1. Let us say find the true collapse load of a propped cantilever subjected to or under uniform distributed load. Okay. Let us take an example where static theorem is applied. We will choose static theorem now. So, let us take a cantilever which is propped at one end, subjected to uniform distributed load W per unit length. Let us say the span of the beam is L and it has got EI properties. Let us call this section as A and this as B. Now, we really do not know where will be the maximum moment happening in the span AB. Let us call that section CC and we want to find this. So, it is that section where the moment is going to become maximum. Obviously, I think it is very clear for all of us that CC cannot be at the mid span because one end is propped, other end is fixed. So, there will be an uneven distribution of the critical section, it cannot happen at the midspan. So, by the way, let us see what is the degree of indeterminacy of this problem, neglecting axial deformation. So, let us say there are two reactions at A and there is one reaction at B, is it not? So, now the total is 3, equations of static equilibrium is 2. So, I need the number of plastic hinges to be 2. Where will they form? They can form at A and they can form at C, they cannot form at B, okay, because B is already a hinge where the moment is 0. So, now it is very important to locate the section C, is it not? Then only we can. So, now the problem is I cannot draw quickly a statically admissible bending moment diagram and locate the hinge because I do not know the distance at which this is going to form. Let me call that as x. So, let me draw the bending moment diagram. So, we know this is going to be MP, this is going to be MP. So, one hinge will anyway form here. So, let us say the other diagram is here. So, the section is going to be CC, which is a distance x from here, okay, and there also the net diagram is going to be MP. So, this is the net bending moment diagram. But the difficulty is what is C or what is x? We do not know this, isn't it? So, the first job is to find out that. So, let us say bending moment at C or at section CC. Okay. So, this is MP, let us call this as small y, okay. This is L. So, use similar triangle, this is L and this is MP and this is Y. So, I want this and of course, this is x. So, for L it is MP, for x it is y. So, y will be actually equal to MP into x by L. So, the bending moment at a critical section MCC will be equal to MP plus y, which is MP plus MP times of x by L, which is MP times of 1 plus x by L, which is MP times of L plus x. That is my bending moment at CC, am I right? Okay. Let us also find out this bending moment from the first principles. We know MCC is also equal to WLX by 2, see here the figure, this is x and this is W, WL, okay, into x by 2 minus W x square by 2, am I right? Just see here, I want to find moment at Cc. So, this reaction is WL by 2 and this is X. Okay. So, WL by 2 I am taking anticlockwise positive. Okay. So, WLX by 2 minus WL square x by 2. So, which will become Wx by 2 L minus x, am I right? So, now this is equation 2, we call this as equation 1. Let us equate 1 and 2. Okay. So, we can easily do that. So, MP into L plus x by L should be equal to, okay, should be equal to Wx by 2 L minus x. So, I can straight away say MP is W by 2, okay, into XL of L minus x by L plus x. Can I say this? Equation 3. This is XL. Okay. Now, for this bending moment to be maximum, the first derivative of this with respect to the variable should be 0, is it not? Because we want the bending moment to be maximum here. So, differentiate this, set that to 0 and find x. If you solve that very quickly, you will find x as 0.414 L. I will write here by solving we get. It is a very simple problem, I should be able to solve. Once I know x, let me find MP. So, substitute in equation 3, we get MP as which is W by 2 XL L minus x by L plus x, which will become 0.086 WL square. You can try and see, is okay. So, therefore, WC is now going to be 11.66 MP by L square, or WC into L will be 11.66 MP by L, where this I can say as capital WC 11.66 MP by L. So, friends, you can see the procedure of finding out collapse load. If the system is complicated and you cannot draw the statically admissible bending moment directly to locate the plastic hinges, then the solution is tricky. So, you know, in this case WC is given by 11.66 MP by L, and we all know very quickly that MP is sigma y into Zp. Sigma y for the material is known, Zp for a cross section is known, because Zy into shape factor is known. So, the right hand side of the equation is known, therefore, WC can be computed. So, collapse load is estimated. Okay. So, look at this example very quickly, that how we used the static theorem in a roundabout manner to estimate the collapse load. In the earlier examples, they were straight away because no such complication was there. I could easily draw the statically admissible bending moment diagram and mark the required number of plastic hinges readily at those cross sections and get the collapse load directly. But in this case, I could locate the section, but I do not know where it will happen. Okay. So, I found out that and I could locate this, right. Let us try to solve the same problem using kinematic theorem. Let us see, is it easy for us to use kinematic theorem in this case? So, kinematic theorem says for a propped cantilever under uniform distributed load over a span of LEI, I have to draw the mechanism. We know the degree of static indeterminacy in this case, let us say this is A, this is B and this is C. So, we know there are two unknowns at A plus one unknown at B. We are neglecting the axial deformation. Equation, this is equation will be minus number of equations. So, equation of equilibrium will be 2. So, number of plastic hinges required will be 2, because the degree of indeterminacy is 3 minus 1 which is 3 minus 2 which is 1. So, I need 2 plastic hinges. Where will they form? They will form at the fixed support, they will form at C, but C location earlier was not known using the static theorem. Now, I know this. So, I get hinges here and here. Now, I can draw the deflected profile and draw the hinges. Say this is theta 1, this is theta 2, this is theta 1 plus theta 2. Okay. So, from the figure we know theta 1 is 0.586 del, this is del. So, tan theta 1 is theta 1 for front deformation is del by 0.586. Okay. Then theta 2 is del by 0.414 L. Okay. So, let us say the external virtual work is half into base into height into WC. The internal virtual work is MP into theta 1 at A plus MP into theta 1 plus theta 2 at C, which will now MP theta 1 plus MP theta 2. Let us substitute for theta 1 and theta 2 from here, which will become 2 MP times of del by 0.586. Oh, let me do it in the next line. Next slide, which is say here internal virtual work will be 2 MP, theta 1 is del by 0.586 plus MP times of theta 2 which is del by 0.414 L. Okay, which becomes 5.828 MP by L of del. Okay. So, by equating external virtual work to internal virtual work, we get WC. Let us equate this. WC into half L del is 5.828 MP by L del. So, del goes away. So, it will come 11.66 MP by L square. or this is small WC, right? WC into L is 11.66 MP by L, which is capital WC. So, friends, you will see that this value is same as we obtained here, but there is a very interesting conclusion in this problem. We have used static theorem solution to check the kinematic theorem solution, is it not? How can you say this? See here, I have borrowed this data from the static theorem. So, please friends note that all the time these two theorems are not independently applied. Some of the problems they are dependent, they will be helping each other. Okay? So, please understand that it is important that I must know both the theorems, how to employ solution finding both the theorems, then only I will be able to successfully find out the collapse load. There is a very standing example we have here. Okay? Let us do quickly a design problem and see how this can be helpful. Let us say a fixed beam with eccentric load of magnitude 30 kilonewton over a span of 5 meters is to be analyzed for collapse load. Okay. So, the beam is here, fixed beam, there is a load which is W, which is 30 kilonewton, and the load is 2 meter from the end. So, this is 2 meter from the left end and this is 5 meters. So, now the degree of static indeterminacy is, let us say this is A, this is B, this is C. So, there are two unknowns at A and there are two unknowns at B, neglecting axial deformation, okay, minus equations of equilibrium. Equations of equilibrium will be 2, that is sigma f y naught and sigma m 0. So, therefore, degree of indeterminacy is 4 minus 2, 2. So, the number of plastic hinges required is 3. Where will they form? They will form at A, they will form at B, they will form at C. So, straightforward solution. Let us draw the deflector profile. Hinge here and hinge here, theta 1, theta 2, theta 1 plus theta 2. So, I could say now the external virtual work is W into del, internal virtual work is MP into theta 1 which is at A plus MP into theta 1 plus theta 2 which is at C plus MP into theta 2 which is at B. So, from the figure one can easily find that theta 1 is del by A which is del by 2 meters and theta 2 is del by B which is del by 3 meters. So, external virtual work is W into del which is equal to internal virtual work which is MP times of 2 theta 1 plus 2 theta 2. Is it not? So, 2 MP times of del by 2 plus del by 3 is W into del. So, del goes away. So, I can find the true collapse load as 2 MP times of 1 by 2 plus 1 by 3 for a given cross section. If I know the shape factor, if I know zy, I can find MP. So, I can find the collapse load. So, plastic analysis is very simple using these theorems if they are not iterative. Okay. Let us say I have, we will do a couple of more problems later. So, let us write down the summary what we learned from this lecture. This lecture helped us to learn example problems to determine the collapse law. We have used both static theorem and kinematic theorem to estimate WC. We have also seen examples where one theorem supports the other in estimating WC. So, plastic analysis is simple, easy, and here the load is function of MP, where MP is a function of material and shape factor. It is a geometric property. Of course, material is also involved. Okay, that is interesting, and I am sure you will find more examples in my book and other literature papers, and you will be able to enhance your interest towards estimating plastic analysis or doing plastic analysis and collapse load estimates for varieties of problems, which we will be doing furthermore in the coming lectures. But however, I wish that you should do more examples by taking these case studies or looking at examples illustrated in my textbook and my reference notes. Thank you very much, and have a good day, friends. Bye.